at Mount St. Helens in Washington State. Earth scientists are learning all they can about one of our century's most spectacular volcanic eruptions. Scientists monitor the volcano day in and day out, studying the mountain from the air and on the ground, searching for new knowledge. When Mount St. Helens began a series of tremendous eruptions in 1980, it gave geologists and other Earth scientists a unique opportunity to study a major volcano in action. This awesome spectacle was not an isolated event, but part of a never-ending cycle by which Earth materials are formed and altered. Part of the rock cycle, which is a fundamental geologic process. Earth is a dynamic planet. Volcanic activity brings violent, radical changes. Changes are also seen in the atmosphere and in daily weather patterns. We live on a water planet. Moving water is the most widespread agent of change. From ocean waves to rushing streams, moving water shapes and reshapes the face of our planet. Water is a key force in the rock cycle. Earth changes are not always as easily seen. At Santa Barbara, California, a cliff rises 10 meters above the ocean. Embedded in the rocks of this cliff are fossils of marine animals, the remains of creatures that once lived on the ocean floor. Over hundreds of thousands of years, this great expanse of coast has been lifted to its present position. These very slow Earth movements often take place where the Earth's plates meet. The plates are great segments of the Earth's outer shell, which are in motion, changing the shapes and positions of the continents and oceans. Where plates meet, new rock may be formed, and old rock changed. On the Earth's surface, rock is altered by weathering and erosion. Within the crust, heat and pressure act on the rock. Molten rock, a superheated liquid, cools on or near the surface to create igneous rock. On the surface, weathering and erosion break down the igneous rock, creating sediment, which accumulates in basins on the Earth's surface. These accumulations of sediment may be changed into sedimentary rock over thousands of years. Sedimentary rock may be broken down into sediment once again by weathering and erosion, or if subjected to increased temperature and pressure within the crust, it may be changed into metamorphic rock. Igneous rock may also be transformed into metamorphic rock. If exposed at the surface, metamorphic rock may be eroded to produce sediment. It may eventually melt to form magma and cool into igneous rock once again. This rock cycle is the key to geologic change on our planet. These changes are triggered and driven by energy. The sun's radiation is a primary source of this energy. Some of this solar energy is converted to kinetic energy of moving water, air, and rock. Earth's interior is another source of energy. Some rocks beneath the Earth's surface contain large amounts of heat or thermal energy. The flow of energy on Earth drives the rock cycle. To understand the origins of heat from within the Earth, we need to go back approximately 4.5 billion years to Earth's beginnings. It is generally agreed that Earth passed through a molten stage shortly after it formed. Over many millions of years, the outer part cooled and solidified. but part of the Earth's interior remains fluid, with higher temperatures toward the center. Molten rock near the surface is called magma. When it reaches the surface, it is called lava. When magma and lava cool and solidify, they form igneous rock. Igneous comes from a Latin word meaning fire. Where does magma originate? The Earth has a solid crust, thicker under the continents than under the oceans. The crust is the upper part of the lithosphere, which extends approximately 70 kilometers beneath the surface. Below it is the asthenosphere, a thick layer of plastic or semi-solid rock. The continental and oceanic plates ride on the asthenosphere. Magma may form where these plates meet, and here the rock cycle begins. Volcanic activity, much of it beneath the sea, forms mid-ocean ridges at the boundaries of oceanic plates. As these plates move slowly away from each other, magma moves upward from the asthenosphere. Iceland is part of the mid-Atlantic ridge, and here a great deal of volcanic activity takes place. In Iceland, volcanic eruptions are fairly common and produce large quantities of cinders and ash. Lava from these eruptions cools to form igneous rock, building new islands. Magma may also occur where two plates collide, or where the crust of one plate dives under another. Volcanoes are found in parts of the west coast of North America, where the North American and Pacific plates meet. Volcanoes may spew out ash and lava which cool and solidify to form igneous rock. Here we see the rock cycle at work. Not all igneous rocks are the same. They display a variety of colors, textures, and mineral compositions. Geologists classify igneous rocks by identifying the minerals and elements of which they are made. Granite is a common igneous rock found on the Earth's surface. Granite consists primarily of the mineral quartz and minerals of the feldspar group. Basalt is a second common type of igneous rock. Basaltic rocks dominate the crust beneath the Earth's oceans. The Devil's Postpile in California is a spectacular basalt formation formed from an ancient lava flow. The column-like structure is the result of vertical joints created as the lava cooled and shrank. Granite is usually lighter in color than basalt. Color and also texture may reveal how and where a rock formed. Basalt cools relatively rapidly and is fine textured. Granite is typically coarse textured with larger crystals, indicating that it cooled slowly. Granite is an intrusive rock because it intruded other rocks beneath the Earth's surface. If the covering rock is less resistant to erosion, it may erode away over millions of years, revealing the granite. Erosion is another step in the rock cycle. Erosion has revealed the majestic granite domes in California's Yosemite National Park. The sedimentary rock that the granite intruded has been stripped away. Lava and magma very close to the surface cool comparatively quickly. Thus, large crystals do not have time to form. This cliff in Yellowstone National Park is formed of lava which cooled so fast that no crystals had time to form. This type of rock, which has no crystalline structure, is called obsidian. It is also called volcanic glass because of its smooth, glass-like appearance. As soon as igneous rock is exposed on the Earth's surface, atmospheric weathering begins. This stage in the rock cycle is already underway at this newly formed volcano on the island of Hawaii. At Shiprock, New Mexico, the overlying rock has been stripped away, revealing the throat of an ancient volcano and spectacular long igneous dikes radiating from the central vent. Physical weathering also results from human activities, which break down surface rocks, exposing them to further weathering. Explosions and earthquakes crack and shatter rock. Rocks may also be split apart by plant roots that wedge into cracks and crevices. Trees may gain a foothold as these fractures enlarge and fill with soil. But water is by far the most significant agent of weathering and erosion. Water works in a variety of ways. When water freezes, it expands. Alternate freezing and thawing gradually enlarge crevices and remove rock particles. Flowing water transports weathered rock materials, thus acting as an agent of erosion. Running water tumbles and breaks rocks and rounds and polishes them. These rock formations are the result of chemical weathering, processes that alter rock by chemical rather than physical means. Water combined with carbon dioxide forms a weak acid which attacks rock. This can be shown by adding a weak solution of hydrochloric acid to limestone. The acid reacts with the rock and dissolves part of it. This process has played a role in forming these sinkholes. Chemical weathering accounts for the deep cracks and fissures of this severely eroded limestone and this sinkhole in New Mexico. Acid-charged water has dissolved part of the limestone and carried it away. Weathering is almost always coupled with erosion, and water is the main agent of erosion. Rain and wind have eroded desert sand, leaving behind these unique features, capped with harder rocks, which protect the soft pedestals from destruction. Erosion is defined as all the processes by which earth materials are loosened and moved on the Earth's surface. In this phase of the rock cycle, moving water plays a major role as it transports earth materials from one place to another. Rivers may be discolored by the large load of sediment they carry as they wind their way toward the sea. Water also erodes the land by means of ocean waves and currents. And in the form of moving ice. Ice acts most powerfully as an agent of erosion in the form of glaciers. Large and slow-moving, a glacier may remove and carry hundreds of thousands of tons of rock debris. Gravity may also be an effective agent of erosion. Eroded materials will always tend to move to a lower elevation. Wind also wears away the land. Wind may carve large rock formations or move a blade of grass, but shapes and erodes the surface of the sand. Wind working with water has helped in the formation of many unusual desert landforms. The end product of weathering and erosion is sediment, rock and mineral fragments transported and deposited by water, wind, and ice. In Death Valley, water carries sediment from mountains down to the desert floor. In the severe desert heat, most of the water evaporates rapidly. Huge expanses of the valley floor are covered with formations of mineral salts, which crystallize from the evaporating water. Deposition of sediment is another key phase in the rock cycle. Sediment may be carried hundreds of kilometers by rivers, eventually to be deposited in oceans. Over millions of years, layers of sediment undergo a transformation. They become sedimentary rock in another step of the rock cycle. Geologists classify sedimentary rocks according to the materials of which they are made. Sandstone, for example, is a clastic rock, that is, formed from pre-existing rock and mineral particles. Some sandstones are soft and easily eroded. Another common type of sedimentary rock is limestone. It is a chemical sedimentary rock, formed of limy materials that have precipitated out of water and later hardened into rock. Like other sedimentary rocks, limestone builds up in layers or strata. In some areas, such as the Glass Mountains of Texas, we find biochemical sedimentary rock containing the remains of marine organisms. This limestone consists of fossils of ancient plants and animals. As these creatures died, they accumulated on the ocean floor, eventually to be cemented together and hardened into limestone. Coal is also a sedimentary rock, the remains of prehistoric plants, consisting largely of carbon, along with water and certain mineral impurities. Sedimentary rock forms by a process called lithification, which begins with the accumulation of sediment. Individual grains of sediment are cemented together by other minerals. Over thousands of centuries, these rocks formed from layers of sediment. The most abundant sedimentary rock is shale, which consists of fine particles of sediment that were compressed and hardened. Shale is a very fine-grained, soft rock. If subjected to still more heat and pressure, it may turn into slate, a brittle rock, which forms thin sheets and splits easily. Slate is a metamorphic rock. Metamorphic means changed form. Further heat and pressure may change slate into schist. Schist may also split easily into plates. Schist has a coarser texture than slate, and during its formation, crystals of new minerals may grow. Gneiss is another common type of metamorphic rock, in which the minerals are easily seen and frequently occur in bands. The formation of metamorphic rock is yet another key step in the rock cycle. Or lava, thus completing the rock cycle. Act on rock. Magma, or molten rock, a superheated liquid, cools on or near the surface to form